Good morning. Today we are going to present the topic 2 of bre261. I'm Hui Chit Kit.
I'm Hui Chit Kit, Kenneth.
I'm Mak Shui Bun, Ben.
I'm Patrick Jr.
I'm Hau Ying, Charlotte.
So today we are going to discuss about the microstructures for two materials, metals and timbers. And then we will delve into something about considering the thermal properties of these two materials. So later in the coming sessions we will have a part measuring the environmental performance of these two materials regarding to the corrosion aspect. Okay, so here I'm going to talk about the microstructures of metals, and to kickstart, I would like to talk something about intermolecular force in metals. So actually, you can see from these photos, every metals inside, you can see there are lots of metal atomic ions and surrounded by a sea of electrons, and all these forms a strong metallic bondings. So you might ask, like, why there exists a metallic bond? So it is believed that the bondings is formed due to the electronegativities among electrons and metal ions. Because when metal atoms transfer into metal ions by delivering an electron, it will transfer from neutral state to a positive state. And since the nature of electrons is actually negatively charged, so that makes up to a huge electronegativity difference. And such electromagnetic inductions has created the delocalized electrons surrounding the metal ions forming the metallic bond. And another features in these metallic bondings is that all the delocalized electrons, they are actually moving around freely. They're not associated with any metal ions. And for the structural arrangement, we will talk about something related to the crystalline structures of metals. And that can only be formed when a metal cools from its molten state or from a heated state. And considering the crystalline structures, it could be formed because of two reasons. The first one is nuclearizations, and then the second one is crystal growth. So to kickstart, to have nuclearizations, you have the homogeneous or heterogeneous nuclearizations. And that depends on whether there's a preferential arrangement for grains, which are small fragments within the crystal structures. And people say, like, homogeneous nucleations refers to a random, distorted merging of grains to form lattice structures, while heterogeneous will have a certain well-organized patterns in it. And then they form the base for the crystal lattice structures. So when more atoms, when more grains add into the structures, they will form the crystal growth. That makes up to lattice structures forming from a small part to a large part. And when it forms into a large part metal crystals, they would be classified into three different lattice structures. The first one is the closed hexagonal structures. The second one is face-centered cubic structures. And the last one is body-centered cubics. So the first one, you can see it has hexagonal columns, and inside on the top layers you have 7 atoms in it, and the same things apply to the bottom layers. While in the middle layers you have 3 separate atoms. And the right-hand side on the slide shows the stacking patterns for the closed hexagonal structures. You can see it has the structures patterns of AB, AB, and AB, and that means every layers within the structures will be exactly located right on top of the depressions for the layers below it. And also every alternate layers will be exactly the same, and they will be the same as what we see when we consider the normal views of the lattice structures. And for the coordination numbers, it will score 12. And by coordination numbers, it refers to the number of atoms or ions immediately surrounding and atoms or ions within the structures. So this is the unit cell of CPH. So within every unit cell of CPH, there will be a total of exactly 6 atoms. So how do we calculate 6 atoms? Well, firstly, we will consider the corner atoms. So there are 12 atoms within lying on each of the corners. So it has to be multiplied by 1/6 because only 6 hexagonal closed path structures can form one single compact structures. And then the atoms at centers would be total independent to define the formations for the structures. So we consider it as an intact one. And so you can see 2 plus 1 is 2 plus 3, and then plus 1 atoms from the top layers and the bottom layers, because the top and bottom atoms will share added together to form 1 atoms. So that makes up to 6. And this is the face-centered cubic structures. So you can see each corners of the cubic structures, you have at least an atom in it. And then on each face of the cubic structures, which contains 6 faces, we have at least 1 atom lying in the middle of it. For the stacking patterns, it would be ABC patterns. So that means every structural layers would repeat the same for every third layers. And every third layers will also be very different to the first layer. So that won't be AB patterns, but instead it will be ABC patterns. So the right hand side shows the normal views for the face-centered cubic structures. And this is the unit cell of face-centered cubics. And you can see there are 6 atoms at each of the corners, at each of the face of these structures. So it has to be multiplied by 1, 2, so it adds up to 3. And then considering 1 atoms at each of the corners, so that makes up to 1 atoms, and together they form 4 atoms. And the last one is the border-centered cubic structures. So it is very similar to the last one, but instead it has only 1 single atom lying in the center of the cubic structures. For the stacking patterns, you won't have any because it is not a closed path structures. It is simply a cubic structures. But it has a coordination numbers of 8 because every single atom within the structures will have immediately 8 atoms surrounding it. So this is the unit cell of body-centered cubics, and it has a total numbers of 2 atoms because all the corner atoms add up to form 1 atoms, and plus the only 1 independent atoms at the centers, so it adds up to 2. And to talk about the steel metals, but actually it is not a single metal. It is a metal alloys, which is defined as a component of irons and carbons. Actually, it can consist of more atoms like nickels, like magnesiums, or other elements, but mostly ions will be the main component within it. And steel is usually formed by rapid heatings of its component and then immediately cooling it. So different temperatures, different cooling rate here would determine what phase these steel materials consist. And normally steel consists of more than 1 phase. So that makes up to multi-phase alloys. And here it has 6 types of phase, like containing ferrite, austenite, cementite, pyrite, bainite, or martensite. So we'll focus on these 3 phases because it happens mostly in steel structures. So the first one is ferrite. It has a body-centered cubic structures, and it is very stable at room temperatures, or even up to 912 degrees Celsius. And for its strength, it's quite high, like 280 newtons per millimeter is found. And it is also very hard because it can withstand about like 80 Bernals in normal atmospheres, and it has a maximum solubilities of carbons around 0.022% rate. And then the second one would be the Y austenite, and the difference between these 2 structures, these 2 phases, would be the Y austenite has a face-centered cubic structures rather than a body-centered cubic structures. And it is formed when the ferrite is heated up to critical temperatures for around 723 degrees. And for its solubilities, it would be 0.8% at 700 degrees around, and 2% at 1000 degrees. The last one is the delta ferrite. So delta ferrite would have very similar properties as the alpha ferrite, and it is formed when the wire austin is heated up to 1400 degrees Celsius. And when this happens, the phase center cubic structures within the austin would transform into the body center cubic structures. And for the maximum solubilities of carbons, it will be the same as the alpha ferrite. So this is the microstructures of steel example. Like here, you can see this is the low carbon steel, and it has a carbon content around 0.1%, and it consists of both alpha ferrite and perlite. So you can see the white regions within this microscopic wheels of the low carbon steels represents the ferrite layers, the ferrite grains, and the dark regions would represent the perlite. So people ask like, what is perlite? Because normally people can't differentiate it. Because perlite consists of similar properties like ferrite, like it consists 88% alpha ferrite, but in addition to it, it also consists 12% cementite. And there are some black dark spores within these microscopic wheels, and they're actually the oxides and sulfides. So on the right hand side, it would be the high carbon steel microscopic structures. And normally it has a very similar property, similar component like the low carbon steel. It also consists of ferrite and perlite. But in addition to it, it also has a higher carbon content. Like by weight, it has around 0.8%, and that is like 0.7% higher than the low carbon steel. For the second metals, aluminiums, it is a thin, it is a metals that consists of a thin, stable oxide layers coatings on its metal surface, and these oxide layers provides very strong, massive corrosion resistant to the metals, as they are very stable at room temperatures. And here you can see this is the electromagnetic diagrams of aluminiums, and it has 14 neutrons, 13 protons, and 13 electrons. And by the 2882 theories, there will be three electrons at the outermost shell of the aluminiums. And since there are free electrons, so the aluminium element is very reactive, and that's why it does not exist in pure form in nature. And this is a part talking about the aluminium structures. So it has a phase center cubic structures, and each grain actually has an isotropic structures. So by isotropic structures, really refers to every grains within the aluminiums to be aligned in a single direction. So that would be a directional alignment, and all this has made the aluminiums an isotropic element. And apart from this, aluminiums also have many dislocations. Like in here, you can see, let's say the atoms that are underlined with red lines are actually the dislocations. So what happens is when stress is applied to the metals, all these single white atoms at white grains will be moved to the right hand side or moved apart from the dislocations. While the dislocations itself will be moved to the boundary grains. So all this has eventually made up to layers of grains will be slipped away by one atomic spacings, and all this has made aluminium very ductile. And the last one is the copper. So copper has a phase center cubic structures, and it is very stable, and that's why it can exist naturally in pure form. And normally, for commercial process, when we produce copper, we firstly crush the copper oils into powder forms, and then we melt and solidify it. So when the golden copper state, when it solidifies, it will form dendrites, which is an open tree-like structures. when copper form crystallizes, you can always see dendrites within it. And dendrites are actually an open space consists of copper and copperous oxide. And when you look at the microscopic views, you can see there are actually dark spots within it. So, and here, I would like to provide you with 4 different microscopic structures of coppers. So the one on the top left is the original structures of copper, and then the one on the right hand side is the structures of hot extruded coppers. So it is formed under annealings. So annealing refers to heatings and then coolings of coppers or metals. And the special features of it is that it consists annealing twins. So annealing twins are fragments within the structures, which has a parallel lines across each fragment. And on the bottom, 2 microscopic structures, they are the coppers under normalizations, and they are also structures of hardening coppers.
Greetings, my name is Ben, and I'm responsible for the introduction of the microstructure of timbers. And to begin with, I would like to first talk about what is timber. Timber is a form of wood that has been processed into beams and parts and often used as construction materials. And throughout the whole human history, timber has been used for over 5,000 years. For example, like this Nanjing Temple of China. It's the oldest building, wooden building in China ever exist. It's already been running and standing for over 1,500 years till now. And apart from that, our wooden furniture in our house is also made from timber too. The advantages of timbers are many. Firstly, it's renewable and also recyclable and also biodegradable. And the performance of timber is largely depends on its microstructure. And the microstructure will determine the timber's properties, like its appearance, structural, and durability. And further determines its specifications, like its size or its gradings, or how to protect these materials. And because timber is a product of wood, so that I think we should also know about the general situation of wood. And wood is a complex biological structures. It's composed of many cells and chemicals to form a living parts. And the outermost layer of the wood is called the outer bark. It's composed of dead cells and also provides a waterproofing layer. And the next layer is the inner bark, which is also called the bone. And its function is to translocate the sugar made by photosynthesis to other parts of trees. It can also provide padding and strengthen the tissues. And the next part is the vascular capillary. In this part, the wood cells are continually divided, creating phloem on the outside and xylem on the inside. Xylem is used to transfer water and provide additional support to the parts. And the more inner part is called the soapwood. And the soapwood is also used to conduct water. And the oldest inner parts of soapwood will gradually change into hardwood, which is the hardest part of the wood. And the center of the wood is the pith, and it is the remnants of the plants before wood is formed. And the next part I will talk about the cells in wood. And the basic unit of wood cell is called the plant cell. And what makes wood cell different from normal plant cell is that wood cell consists of photolith and cell wall. And the cell wall of plant cell is used to support the cell membrane. And they have various parts. And the first part is the middle lamina. And it's the outermost layer of cell wall. And it's the cell wall material that is contributed by different cell materials. And the next part is the pyramidal wall. And it consists large number of cellulose and microfibers. And the more inner parts of the pyramidal wall is the secondary wall. And secondary wall has 3 major parts. I would divide them into S1, S2, and S3. The S1 part is the thin and also consists of large angle microfibers. And the more inner part is the S2 layer. Is the thickest layer and characteristic by the low lining consistent low-angle microfibers. And H3 is similar to the H2 layer.
And wood cells are composed of three main chemicals. And the first one is that the cellulose. It is the long-chain polymer with the chains principally allied to the long axis of the cell. And you can here is the structure of the cellulose. You can see that there are three hydrazine groups and are running position of is C2, C4, and C6. And that means that it is responsible for its properties of that it is hydrophilic and also carable. And the hydrazine group can also form hydrogen bonds within different polymers, so that they could increase the intermolecular force within the molecules. And the next one is called the hemicellulose. It is cellulose-like molecules, but it's not as long as the cellulose chain. And the last one is lining chemicals, and it is formed by CC or CCO bond, and it does not possess any repeating units like the cellulose and hemicellulose. And wood timbers are further divided into softwoods and hardwoods. And softwoods are produced from angiosperms, which means the foreign parts. And on the other hand, hardwoods is produced by non-power parts, the gymnosperms. And the cell structures in softwood is much simpler than hardwood. There are only two types of cells in softwoods, and lead to variations within the structure of the cells. However, on the other hand, hardwoods shows a great variety of cell types, and also are variants in structure of the cells. And the biggest difference is that softwoods has Warsaw elements. However, the hardwood does not have any. And the basic characteristic of timber that relates to its microstructure is that the timber contains growth defects from logs or soaks, and also the fiber orientation will lead to the defects in its strength and stiffness. And you can see that it is a logs examples. And these logs will actually reduce the strength of timber and make the timber more easily breakable. So that before making any timbers, the presence of defects must be recognized and change the design to fit these defects. And apart from that, the strength analysis will also variance within different plant types, and also the tension strength of this timber. And here is a table comparing different timber materials and its tension strength. And you can see that the softwood has actually the highest strength among these three materials. And apart from that, another properties that timbers possess is that it is anisotrophic, and which means that the tension strength of timber is affected by its directions of fiber. And you can see that the tension strength of timber of its fiber direction is actually maybe 30 to 15 times more than its perpendicular directions. And the elastic modules perpendicular to grain could have an 18 times difference in strength. So that you will find that when you apply force here in perpendicular to the timber, it will easily break the timber. But however, if you apply force parallel to the timber, you can hardly break the timber unless you apply a lot of force. And this shows the anisotropy properties of timbers because of its microstructures. And that's all my part. Thank you.
So I'll talk about the thermal properties of these few building materials. In order to evaluate the building materials' thermal properties, we can evaluate from different aspects. For instance, thermal capacity, thermal conductivity, thermal mass, or even thermal expansion. And in this project, we'll mainly focus on thermal conductivity as well as thermal capacity. Thermal conductivity means how a substance is able to transport heat energy from a region of high temperature to a region of low temperature, and it can be calculated by this equation as shown here. And alternatively, it also means heat is transported through either electronic contribution or vibrational contribution. And from this perspective, it can be calculated by this equation. And there are a few measurements for calculating the thermal conductivity of a building materials. There are steady state or non-steady state method. For steady state method, it means the temperature of the building materials will remain constant, and for non-steady state, it means the vice versa. And for the apparatus, we can use hot pulse apparatus or hot plate apparatus to calculate the thermal conductivity of a substance. And this graph shows a hot pulse apparatus for calculating the thermal conductivity. And for measuring the thermal conductivity of building material, we normally use hot pulse apparatus because hot plate apparatus require a smooth surface for measurement, but building material is not necessarily to have a smooth surface. And I'll talk about the thermal conductivity of metal. It is quite high compared to other substances because it has high concentration of free electrons in its structure, and those free electrons can transport heat energy through moving through the lattice. And thermal conduction based on phonon is also occurred. However, this effect is not as large as that of electronic conduction. At specific temperature, the thermal conductivity is proportional to the electrical conductivities, which is according to Franz law, and as shown here. And this is a graph showing the relationship between the thermal conductivity and also electrical conductivity of metals, and you can see that they are proportional. At low temperature, the heat is carried through free electrons, and the mean velocity is the thermal velocity in this case, and the mean free path is temperature independent. However, at high temperature, phonons limit the mean free path of the metals, which leads to the decrease in thermal conductivity. And we can draw the conclusion that is the thermal conductivity of metals has a decreasing trend with increasing temperature. As shown here, you can see that for lower temperature, the thermal conductivity is very high, and it drops when the temperature increases. And the thermal conductivity of copper is 385 mole per meter K, and aluminum is 205, steel is 50.2. And for the thermal conductivity of timber, it is quite low. This is due to the special structure of the timber, because there are air pockets within cellular structure in timber, and the thermal conductivity for timber, its thermal conductivity increases with density, which means that the lightweight timber is the best thermal insulator. The thermal conductivity of wood can be calculated using this equation, as shown here. And the thermal conductivity of timber actually varies when temperature changes, just like metal. However, the way of changes is different from metal. We can see that when the temperature increases, the thermal conductivity of wood also increases, unlike metal. And the thermal conductivity of timber also varies with moisture content. When moisture content increases, the thermal conductivity also increases, just like this graph shows here. This is moisture content, and this is the conductivity. And the thermal conductivity of timber also varies with different species of wood. For average thermal conductivity, it is around 0.14 watt per meter K. And for instance, for hardwood log, it has a thermal conductivity of around 1.12, and for softwood, it has around 1. So I will move on to the comparison of thermal conductivity of metal and timber. We can see that the thermal conductivity of copper is the highest among the three metals, while the thermal conductivity of timber is the lowest among the few building materials. And we also conducted an experiment in the Hong Kong Polytechnic University to show the comparison of the thermal conductivity of the few building materials. And here's the setup of our experiment, and this is the result of our experiment. From left to right, this is aluminium, steel, copper, and then timber. And you can see that the rate of heat transfer is the fastest for copper. This is copper, and the heat conduction is the lowest for timber. And this experiment shows the same result from the data we collected. So how about heat capacity? Heat capacity means the ability of a material to absorb heat from the external environment, and it also means the amount of energy needed to rise the unit of temperature. It can be calculated through this equation. And heat capacity can be measured under two conditions, which is constant volume or constant pressure. However, the magnitude of the thermal conductivity at constant pressure is much larger than the constant volume. And the thermal capacity and the temperature are correlated. At low temperature, the relationship of the capacity and the heat temperature can be shown through the following equation, this one. However, this relationship is only shown in the low temperature. And when the temperature is high, the capacity becomes independent of the temperature. Just like the graph shows here, you can see that when the temperature is low, the conductivity also increases when the temperature increases. However, when the temperature is high, there is no more relationship between the conductivity and also the temperature. For the heat capacity of metals, it is mainly due to the atomic vibration and also thermal excitation of electrons. And the valence electrons of metal would have received energy from heat energy in order to contribute bulk specific heat. Only small fraction of electrons of the thermal level contributed to the heat capacity, which means that it is small and not significant at room temperature. And the electric contribution to the capacity is proportional to the temperature, just like the equation shown here. And these two graphs shows that thermal capacity of metals increases when the temperature of metal increases. And from data we collected, we found out that the specific heat capacity of aluminium is around 0.897 joule per gram K, and copper is 0.385, steel is 0.466 at 25 degrees Celsius at constant pressure. For heat capacity of timber, it has high heat capacity, specific heat capacity. The thermal conductivity of timber is around 1.7 joule per gram K at 25 degrees Celsius. And the cellular structure of timber, that it has a myriad of hydrogen bond group leads to timber of having a high specific heat capacity. However, the heat capacity of timber is also affected by temperature and also moisture content, and the accurate heat capacity of timber varies according to different wood species, and the heat capacity of timber can be calculated through this equation. So I'll do a comparison between timber and also the few metals. And see that the thermal capacity of timber is higher than that of aluminium, copper, and steel. And timber has the lowest thermal conductivity and as well as the highest thermal capacity. And the thermal properties of the three metals are quite similar, while copper has the highest thermal conductivity and the lowest thermal capacity, which is exactly the contrary of timber. And the differences in thermal properties leads to their differences in the application of these few building materials. For timber, since it has good thermal insulation, it has the ability to stay cool even under hot weather. Under cold weather, timber loses heat in its low speed, and this means that timber is an extremely good building materials for construction in some extremely hot places like desert. And timber is also used for making ceilings and also wall coverings. And for metals, its usages varies. Like for instance, for copper, it is used as a building material because it has a low thermal expansion and also high melting point. And sometimes the thermal properties of metals is considered as a disadvantage because the heat loss rate of heat loss is very high for metals, and this may not be good for building some structure during for the construction of a building.
Okay, now I'm going to talk about the environmental performance of the metals, which is concerning the corrosive natures. First, I will define what corrosion is. Corrosion is defined as an irreversible reactions. It is the gradual deteriorations of the metals through the interaction between the metals and external environments. It is also regarded as an undesirable phenomenon because it will destroy the luster and the beauties of the materials. Not only about the appearance, also about the functions. The corrosion can also shorten the life of the metals. After defining what corrosion is, I will talk about the cause of the corrosions. It is a spontaneous reactions. Nowadays, we are using the metals, but actually they are not at the original status. The original status in the earth of metal is in their aura status. We have to extract them to become the metals. During the extraction process, a lot of energies will be supplied for the process, so that metals can be regarded as in a energy unstable status, while the aura is the more energy stable status. So that the metals are under the high energies, and they will tend to lower their energies by reverting back to the aura status, so that corrosion can be also regarded as a tendency from the metals revert from a high energy status to the low energy status. Corrosion can be defined mainly into two reactions, which is the electrochemical reactions. It is also known as the red corrosions. Also, it can be defined as the chemical corrosions, which is the dry corrosion. First, I will talk about the electrochemical one. For the electrochemical corrosion to occur, three elements is crucial to present and interact with each other. First is the anode. Anode is the meaning that the sign readily release electrons, which is usually the metals. And the cathode readily accept electrons, which is usually the oxygen. And finally is the electrolyte, which allow the electrons to flow freely, which is usually the water or the moisture in the air. After these three elements interact with each other, will produce the oxide or the salt of the metals, and the products will form on the surface of it. Let's take the corrosion of iron as an example. The water is serving as an electrolyte. The oxygen receives the electron released from the ions, and the rust as the product formed on the surface of the metals. And then I will talk about the dry corrosion. Dry corrosion occur when there is no moisture or water to aid the corrosion process. The main difference between chemical and electrochemical corrosion is the presence or not of the moisture or the waters. And the chemical corrosions, it will oxidize by the atmosphere gases such as oxygen, sulfur dioxide, and hydrogen sulfide. When the metals react with these gases in the atmosphere, similar to the electrochemical corrosions, it will produce similar products, which is the oxide or the salt of the metals, or similarly it is formed on the surface of the metals. Okay, after talking the type of corrosions, I will talk about some factors affect the corrosion rate. Firstly is the natures of the metals of the metal oxides. First, talk about the natures of the metals, how it affects the rate of corrosions. It is actually related to the metal reactivities. The higher the metal reactivities, what is the meaning of that? It means that they will lose electrons more readily. They will tend to release the electrons. And for the lower in the metal reactivities, they they will tend to not release the electrons, so that they lost electrons less readily. According to the metal reactivities and according to the previous page, we see that the anode, which release electrons, is a crucial factor for the corrosion to occur, so that the rate of releasing electrons can affect the rate of corrosion. To sum up, when higher the reactivities mean that the lost electrons more readily, and so that the faster the corrosion rate. However, when talking about corrosion, we cannot only depend on the natures of the metals. We have to consider also the natures of the metal oxide formed. If the metal oxide formed and mainly two characters can affect the rate, as the stabilities and the solubilities of the metal oxide. If the metal oxide formed is stable and insoluble, it can serve as a protective layer, and so that this protective layer can prevent the further attack of the O2 and the waters. It can prevent the corrosion occur. However, if the metal oxide formed is unstable and soluble, it will form a protective. It cannot serve as a protective layer, and the metals will further attack and further corrosions. Let's take aluminium and steel as examples. Aluminium is higher in the metal reactivities. However, it is considered to be more corrosion resistant because the metal oxide formed is stable and insoluble in nature, so that it can prevent the further attack of the corrosions. However, for steel, the metal oxide formed is unstable and soluble, so that it will further attack. To sum up, which means we have to consider both the natures of metal and the natures of metal oxides when concerning about the corrosion rates. Also, pH is another important factor. Why pH can affect corrosion rates is closely related to the previous part about the solubilities of the corrosion products. The pH will greatly affect the solubilities of the corrosion products. First, let's take a look at the case of aluminium. We talk about aluminium at the natural status. It has the metal oxide formed can serve as a protective layer because it is insoluble in the natural pH environment. However, when in extreme low pH or extreme high pH, the metal oxide formed will become soluble, and hence the rate of the corrosion will increase in the extreme pH environments. And then we will talk about the case of irons. Irons, lower the pH value, which means more acidic the environments. The steel oxide formed will become soluble, and hence the rates become more faster. However, in the extreme alkali environment, the metal oxide formed become insoluble, so that the rates become lower. After talking about the natures of metals and oxide, we'll talk about the presence of the other salts. For example, the presence of other salts such as sodium chloride, which means we always see that as the seawater. The presence of other salts can increase the conductivities of the aqueous solution, which means the electrolytes. When the conductivities of the aqueous solution increase, the rate of corrosion will increase too, because the electrons become more flowing in a more faster rate. After talking about the factor to affect the corrosion rate, I will talk about the type of corrosion. Uniform corrosion, localized corrosion, and galvanic corrosion as the three common type of corrosion. First, I will focus on the uniform corrosion. It is also known as the general attack corrosions, which the corrosion rate is constant over the entire surface or the large proportion of the surface. The thickness is reduced by a uniform amount. However, compared to the localized electrons especially target one areas of the metal structures. So that there will be a different rate of different rates of corrosion in different parts of the metals, so that it will result in an unbalanced thickness reductions. So after talking this too, we will focus on the galvanic corrosion. It is also known as the dissimilar metal corrosions. It will occur when two metals with different reactivities are placed together and exposed to the external environment. The more reactive metals will corrode at a faster rate than it alone. That means it's become a sacrifice metals. It sacrifices itself to protect the less reactive metals. And the less reactive metals will corrode in a slower way than it alone. This is the three main types of corrosion. And now I will talk about the effects of the corrosion. First, it will reduce the metal strength. Why it will reduce the metal strength? It is because the weak oxide or the salt is formed to replace the original strong metals. Now we can focus on the case of aluminium. It is showing how the corrosion affects the ultimate strength, which is the strength the metals can withstand, become shredded or become compressed. You see that when the corrosion occurs more, when the mass loss of the aluminium become more, the strength become more decreased. So that it can see that the corrosion can actually reduce the metal strength. Also, it can affect the metals in the system components. One of the examples is the concrete spalling. Because the rust formed of the steel bar is higher volume than the original iron, it will force apart the adjunction part of the concrete. Force apart the adjunction part. The concrete will break away from the corroded steel bar, so that the concrete will fall down, and the corroded reinforced steel bar will expose it to the external because of the rusting. After that, I will talk about after talking about the safety issues, I will talk about the economic aspects. As mentioned above, corrosion can actually cause serious impacts to the safety. The daily inspection and the maintenance is important to ensure the proper performance. However, it can be a costly or time-consuming process. According to the figures, it shows that different industries have been affected by the corrosion of metals, and in the case of US, 3.1% of the GDP have been lost because of the corrosion problem. Lastly, as we can see, corrosion can cause many problems. How we detect is very important. First, I will talk about the small-scale detection methods, which usually used in the school lab is the rush indicators. The rush indicator is actually the potassium hydroferrate in solutions in the warm gel. When the corrosion occurs, the warm gel will form the blue color with the Fe2+ ions, which come from the very beginning of the corrosion process, so that the appearance of the blue colors actually indicates the rusting occur. And the second method is the radiographic testing. It is the usage of the electromagnetic beams with short wavelength and high energy. Because of the high energies, it can penetrate through the metal easily. When the beam passes through the test samples, some energy will be absorbed, so that we can see that thicker the metals, lighter the spectrum will be shown on the screen. And for the thinner part of the metal, thicker color, because less energy is absorbed. Using these properties, less energy will be absorbed, and also apart from the thickness, the different materials will have different absorption rates. For the corrosion product, it usually absorb less energies, so that they will see the dark color on the spectrum. So according to this, we can determine the thickness if it is reduced by the corrosion, or we can detect the interior corrosion occur or not. Another method is the ultrasonic testing. Similar to the radiographic, the principle is similar. However, it is utilized of the sonic rays with high frequency. It will propagate and reach the back of the tested samples and then reflect back. The time traveled by the sonic waves is actually entering the thickness of the metals. Similarly, when determining the thickness, are the thickness even in the whole metal, we can see that is there corrosion occur to reduce the thickness. Also, if there is the interior corrosions, part of the sonic wave will reflect back by it, so that we can observe from the screen to see where the corrosion occur or not.
I'm Yuk Kwong. Now I'm going to talk about the protection methods for metal corrosion. There are 6 concepts for preventing metal corrosion. First of all, about the removal of oxidizing agent. Boiled water treatment is a method, and when the metal is put into boiled water, the boiled water has lower oxygen content, and metal would have less chances for the rusting process. But this is not applicable to daily application for the construction usage. The second concept is the prevention of surface reaction. It's to prevent the metal from corroding through cathodic protection. Cathodic protection refers to a higher reactivity metal directly contacting with another metal, and the less reactive metal would have less chance for corrosion. The third one is the inhibition for surface reaction. The methods included chemical inhibitors and pH control. They can slow down the rate for metal corrosion, but not completely stopping it. The fourth one is the application for protective coating. There are three types of protective coating: organic coating, metallic, and non-metallic coating. The organic one is about the paint and grease. Paint is for the fixed equipment, and you can add as a barrier to protect the metal from corrosion, from preventing it to directly contact with water and oxygen. And the grease method is for the movable parts of some metals. And the metallic coating includes electroplating and galvanizing. Galvanizing is the plating of zinc, and it can also protect the metal from corrosion. And the non-metallic part is like anodizing, which is a metal oxide layer formed on the metal to protect it from corrosion. The fifth one is the changing for metal composition, such as making alloys like stainless steel. And the sixth one is changing the metal surface conditions. Through maintenance and design, the corrosive elements can be removed on the surface of the metal, so that the metal will be less prone to corrosion. Now I'm going to talk about the steel corrosion protection. Steel is commonly used as the reinforcement bar or formwork for construction. And in construction usage, hot dip galvanizing is very common for the protection of reinforcement bars. It provides barrier protection and cathodic protection to the reinforcement bar. Through galvanizing, the zinc can preventively lose electron because it is a higher reactivity metal, and the iron of steel would be less likely to face corrosion. And this hot dip galvanizing procedures requires high temperature of 430 degrees Celsius, and even though the zinc plating may fall off in the long term, the cathodic protection can still protect the metal from being corroded. And the next one is the epoxy coating. It's a barrier protection because epoxy is a plastic organic material, and it is not as good as hot dip galvanizing because it has some drawbacks, such as it requires special handling to put on the coating, and also the coating is prone to UV damage. Also, after adding coating, the reinforcement bar would have poor abrasion resistance and bonding to a concrete. Hence, hot dip galvanizing would be a better choice. The last one is stainless steel. It contains at least 10% of chromium added to the normal steel, and the chromium added can lead to a formation of oxide film, which prevent the contact of iron with the water and oxygen outside. And the last one is painting, which is very common for steel structures exposed to air, and it can provide barrier protection and good appearance, but the paint might peel off after a long time. Now I'm going to talk about the aluminum corrosion protection. It in construction, aluminum is usually used for window frames and scaffolds. And the possible corrosion which can happen to aluminum is galvanic corrosion, which means that when a metal with lower reactivity is placed next to in contact with aluminum may face corrosion. And the aluminum has a naturally present aluminum oxide layer. And through anodization, the aluminum oxide layer can be thickened. And it makes the aluminum resistant to corrosion. And the chemical reaction shows that at the anode, the aluminum oxide layer is formed. And the thick aluminum oxide layer has some benefits, such as aesthetic benefits, which the oxide layer can be easily color dyed. And there is the typical anodizing cell shown. Now I'm going to talk about the copper corrosion protection. Copper is a relatively unreactive material, and the corrosion problem is less serious. And there are mainly two methods for preventing copper corrosion. The first one is the surface coating. Through tin plating and nickel plating, it provides barrier protection and also cathodic protection. Because tin and nickel are more reactive than copper, then they will preferentially lose electrons, so that copper is less likely to corrode. And through painting, it reduces the direct contact of copper and water and oxygen. And plastic coating includes an organic layer. And for example, for the epoxy pipe lining, which is shown on the right of the picture, is for the copper water pipe. And when a layer of plastic is placed in the inner layer of the copper, the water is less likely to contact with the water pipe, and the corrosion can be reduced. And about the corrosion inhibitors, its principle is to change the properties of the metal surface to suppress the electrochemical reactions. There are two categories of inhibitors, which is organic and inorganic. And about the organic inhibitors, the effectiveness is shown below. The inhibitors containing sulfur is better than the ones containing nitrogen and oxygen. It's because that with lower electronegativity, there is an easier polarizability, and it allows the strong inhibitor metal bond, and it is good for the corrosion prevention of copper. Now I'm going to talk about the environmental performance of timber in terms of its degradation. There are four aspects, which are biological, chemical, physical, and also radiation. I'm now going to focus in the biological and chemical aspect. For a chemical degradation of timber, it means the hydrolytic degradation, which involves the acid hydrolysis of cellulosic materials. And the cellulose would be degraded to glucose, which harms the structure of timber. And it would lead to the decrease in strength and peeling off of paint on the painted timber. And compared with metal suffers from redox reaction of corrosion, while timber does not have chemical corrosion. It suffers from degradation mainly through biological factors. And I'm now going to talk about the weathering and fungi attack to timber. We can see that when there is alternative wet and dry condition, or alternative high and low temperature, the timber will swell and shrink alternatively, and it leads to the cracking of timber. And through the prolonged exposure to sunlight, UV light also breaks down lignin and leads to the degradation of timber. And the third one is the fungal attack, which shows the enzymatic breakdown of cellulose, leading to the degradation of timber. There are two types of fungi related to the attack, such as dry rot, its minimum moisture is 20%, optimum temperature is 23 degrees Celsius, and the fungi will die at 40 degrees Celsius. While for the wet warts, it requires long-term damp condition for the fungi to grow. And the optimum moisture is higher than dry warts, and the optimum temperature is lower. I'm now going to talk about the symptoms of timber degradation. It includes roughened surface of timber due to weathering, and also the dark color areas may fade and the light color area may darken due to weathering. After the fungal attack, dirty spots may also appear on the piece of timber surface, and the following symptoms may also occur, which includes cracking, warping, splitting, and also swelling of the timber, and it leads to some cracks on the timber, and the structure is not safe. It is now for the prevention of timber degradation. Through a surface coating on the timber, such as a water-repellent preservative, we can use wax and paraffin, and it can prevent the water penetration into the timber, and it lowers the chance of weathering, and also fungi will not attack the timber when the moisture is lower than 20%. High temperature can also kill existing fungi, and for testing of moisture content, there is a direct method, but it is destructive, which is taking the wood sample out and measure its normal weight, then dry it out for the dry rate. And for the indirect method, it is to measure the thermal conductivity and electrical resistivity of the timber to know whether the moisture content has exceeded the normal level, which may lead to timber degradation. After introducing the metal corrosion and timber degradation, we will now have a comparison between them. Metal corrosion is a redox reaction with the presence of water and oxygen, and metal is vulnerable to the chemical corrosion. While for timber degradation, it's not caused by chemical corrosion. It is, however, prone to the biotic factors such as weathering and fungi attack. And as timber degradation is not caused by chemical corrosion, we cannot compare the short-term and long-term environmental performances of metal and timber in terms of corrosion. After knowing the metal corrosion and timber degradation, we have the following summary, which is that the accumulation of moisture is not preferable for both metal and timber, and metal and timber will both suffer in appearance and strength when they face degradation. And last but not least, the symptoms observation and also the prevention treatments are very essential to protect the safety in structure of the metal and also the timber, and for preventing their degradation and corrosion. Thank you. And these are our references.